Okay, so we will discuss the energy equation today. As I said, this is pretty much similar to the Bernoulli's equation, but it is more comprehensive. And at the same time, it is derived in a different way. But at the end, you will see they are kind of having the same expression because it's about the energy in a system. So Bernoulli said for any fluid particle, there can be three different types of energy. One is kinetic energy, one is gravitational potential energy, and another one was due to pressure. Here, we are saying like the total energy for any fluid system, it's for system, and the Bernoulli's equation was for a single particle. So for any system, the total energy can be broken into three parts. One is the kinetic energy, which is due to the motion. The next one is the gravitational potential energy. Again, it's due to the elevation against the gravity. And the last one is the internal energy, which is due to the very like microscopic level movement of the particles and the vibration of the particles. Okay, so these are the three different types of energy can be found in any fluid system. And in your copy, there are some blank spaces. Make sure you write down the names on those blank spaces. Now, from the thermodynamics law, we also know that the total rate of change of energy is the summation of rate of change of the heat and the work done within the system. Okay, so we need to know a little bit about heat and what kind of work done in the system also. So that is the next one. The heat energy is like when you apply some heat, obviously the system will have some extra energy. When a system is being cooled down, that means it's releasing heat from the system. That means it's losing the energy from the system, right? Now for the work, there can be three types of work. One is the flow work, one is the shaft work, and the number three is the shear work. So let's go through very quickly what is actually flow work. So flow work, it's actually work due to pressure. And just think about a fluid particle here, okay? Oh, I think I found I kind of found the reason of that extra line. Most probably it's the CPU's power or something. It needs more power, I guess. But I didn't check with other computers, but I think that can be a reason why we are having those extra lines. Okay, so this is a fluid column. And so this is filled with fluid. So when something is like going inside that fluid column, that is actually work done on the system because you're pushing the fluid on that system. And when that fluid is going out of this fluid column, that is actually work done by the system because the system is actually pushing the fluid to going out from this fluid column. So there are two things, work done on the system, work done by the system, and all of these are actually included in this flow work, okay? The next one is shaft work. Shaft work is a work done by the shaft. So pump can have shaft, turbine can have shaft. So this shaft work is basically like work done by pumps or turbines, okay? And the shear work is, you know, that is from the shear stress of the fluid. It can, that is one type of work, but if the fluid, like the surface, like the fixed, if the control surface is fixed, this work is zero. So that is zero for fixed control surface. But if the surface is moving or if the surface is like changing, like it's expanding or shrinking, then there can be shear work. But for the fixed control surface, that is 0. Now, just combining the first law of thermodynamics and the Reynolds transport theorem. Do you remember the idea of Reynolds transport theorem? I gave such a good class example, still you forgot that. So we had a classroom, you came and you were like so pissed off, you jumped off, and some of you inside the class were sleeping or doing something else. So that is basically like some fluid particle is coming in, something is going out, and something is happening within the classroom or the control volume. In total, that is the total rate of change of something, right? It can be mass, it can be momentum, it can be energy. That was the Reynolds transport theorem. So combining that one and the first law of thermodynamics, we can have an expression for the conservation of the energy for the energy system. And I'm writing down that expression. You should have blank spaces, write down that on your copy. So it should be Q in W pump. We will write down what each individual term means. At this point, just write down the equation. Turbine equals to P over, that is P over rho square over 2 out minus P over rho square over 2 C U in. Okay, I will write down the same equation. I will just remove the parentheses and I will use the out for individual term and in for individual term, because that's how I need to use in next expression. So basically it's the same thing. I will just remove the parentheses. I will write down P out rho out V out square over 2 okay, and P in rho in V in square over 2 okay. So you should okay. So that is the expression for energy equation per unit mass, right? Okay. So let's write it down what the individual term means here. You should have some blank spaces in your copy. Everyone's done with this one? Okay. So the Q in is the rate of heat added or transferred into the system per unit mass. W pump is the shaft work per unit mass performed by the pump. That's why the subscript pump. W turbine is the shaft work per unit mass performed by the turbine. And the U is the internal energy per unit mass, okay? And if you look at the expression, you will see it's pretty much similar to Bernoulli's equation, except this time we have some term for heat for pump, for turbine, and something, a new term, which is for internal energy, right? Okay, so this equation is for steady flow, one-dimensional steady flow, which is great because we are not doing anything unsteady in this course. And this equation applies to both compressible and incompressible fluids, so which is great. This equation can overcome all the limitations we had in Bernoulli's equation. If you can remember, we can't use Bernoulli's equation for compressible one. At the same time, we can't use the Bernoulli's equation for the inviscid fluid, viscid fluid, like when the viscosity is very high, but we don't have that problem here. At the same time, it also differs from the Bernoulli's equation because it is derived from an Eulerian approach to a finite volume of fluid rather than a single fluid particle, which was the basis for Bernoulli's equation. Though we came from two different approaches, but eventually we'll come up with kind of similar expression. And since this equation it can be used for compressible, incompressible fluid, so this is the most comprehensive energy equation you can have for steady flow, not for unsteady, only for the steady flow, okay? Now the equation was for per unit mass. We will convert that into unit per unit weight, but before that, do you remember a little bit about laminar flow and turbulent flow? Just a little bit, like laminar flow was the calm and quiet flow. It was like all the parallel streamline. And for the turbulent flow, it was so chaotic. Yeah, and obviously whenever there is a chaotic, there will be a heat, right? When there is a conflict, there will be heat or some heat, there will be a heat energy or something like that, right? So that will increase the fluid's internal thermal energy per unit mass, okay, due to that friction. At the same time, we already had Q in and Q out in the system. So we can name all of these thermal energy per unit mass terms as energy loss per unit mass, FL, okay? So I will write down the equation again, and this time we will use FL instead of U in, U out or something. So what I will do, I will rearrange the equation first so that you can. So I will move all the in left side. Okay, and W pump was already there, so I will keep this one here. W turbine was here. I will keep all the out term on right side. And U out, U in, and I will move this term on the other side also. Okay, so I just rearranged the whole equation and kept all the thermal and internal energy terms all together. And what is the collective name of these three terms? FL, or energy loss per unit mass. So the next expression will be P in, rho in, V in square over 2 plus 2 In the back, can you see the lines and everything? I'm a little bit out of space here. That shouldn't be a problem. FL, okay. So this is a little bit concise, more concise than the previous one, okay. Now we can simplify it more. For incompressible fluid, the density doesn't change, right? For water, it will be always 1000 kg per meter cube or 1.94 slug per feet cube, right? So it will not different for inlet and outlet. So that can be one simplification. And due to PowerPoint, it came out as Q. That should be P in, P out. So one simplification can be P in over just gamma V in square over 2 equals to P out over gamma 2G FL. Okay. Okay. So this equation, the energy equation was per unit mass. We want to express this equation as per unit of weight, because that time it will be head and it is kind of easier to measure and do all the calculation. So you already know, if we want to do that, convert that per unit weight, what we need to do, we will just need to divide by G, right? Okay, so let's do that. Again, P in here. So turb means turbine, I just made it short. Equals to rho out right? Now we know energy per unit weight is actually called head. So each term will be some sort of head, and you can name this one as pump head, this one as turbine head, H turbine. Okay. Also, you can name this one as, since everything is for friction loss or energy loss, it can be the head loss. Okay. So the final form can be P in over gamma, P in square over 2G Z got cancelled, Z in, H pump, H turbine, equals to P out gamma 2G, Z out. Okay. So that is the equation for incompressible steady flow. For compressible one, we can go back to the previous one and maybe we need to use Y rho in, rho out, because that will be different for compressible one. But that is the equation most of the time we will use. Now, you can see how comprehensive it is. You can consider about pump and turbine and all the head loss. Now, two things here. Are you seeing we are adding the energy for the pump, but we are subtracting the energy for turbine? That's because that is the function of turbine, that it will take the energy from flow and convert into something else. The very good example will be hydroelectric power plant. So in hydroelectric power plant, what usually happens? Like, how do you get electricity? What is the method? That means the water is providing energy to the turbine, right? And then the turbine is making that and like converting that energy into electricity. So that simply means turbine is actually taking energy from the system. But when you add pump and you connect that into the like electric outlet, that means the electricity is converting something energy into the flow energy, right? And that's why we can say pump provides energy to the system and turbine takes away energy from the system. And that's why for turbine, we use negative, because that is the amount of energy it is taking from the system. And for pump, we are adding positive sign. Okay. Okay. Now, once we are done with this one, we just need to cover two more things. Whenever we have a pump or turbine, obviously we are concerned about the power, like what amount of power it can provide, right? So we need to know how can we calculate the power for pump or turbine. And whenever you have power or any mechanical thing, you need to know the efficiency also, because in real world, you can't get 100% efficient system. There will be always some sort of loss. So we need to make sure what amount of loss you are having for any system. Okay. Are we good up to this point, everyone? You are done? Okay. So power is actually work done per unit time. That is the power. And power is measured in watt in SI system, you know that, or in feet lbs for FPS system. But maybe you never heard about feet lb per second, but I'm sure you heard about horsepower, right? Like when you go to buy a pump or any car, obviously you check what is the power of the engine in horsepower, right? So you know the horsepower. So horsepower is not the standard unit, but it is widely used unit. So what you can do, you can just divide that feet lb per second by 550, and that will give you 1 horsepower. Okay, so we will do that. So we can express the power in terms of head. Power equals to gamma Q head. Okay. Now this head H, it can be pump head or it can be turbine head, depending on for which shaft thing we are trying to get the power. Also, there is another note here. It can be head loss also if you are trying to find the power to overcome the head loss of the system. So what I'm trying to say by using this sentence, like when, suppose you're designing for a plumbing system for a community. So you need to make sure each household, they get the enough power, enough velocity, everything, right? In other words, the enough energy to work, to do their work. Now, obviously, in any real system, there will be loss. And from the upper end, like from a supplier end, you need to make sure that you overcome that loss, right? So that's why you need to provide some extra energy or something to overcome that loss. And to calculate that, you can use head loss instead of head pump and head turbine. So it will be the other word, this will be any type of head you are trying to work on, okay? Gamma is what? Density, density times G, and that is the specific weight of what? Fluid, right? And what is Q? What type of flow? The volumetric flow rate. Also, we can write down A times V. V has to be perpendicular to the A. Okay. And without seeing the next slide, can you tell me how can you calculate the efficiency? What is the main idea of efficiency? If I say this system is 90% efficient, what does that mean?
10% energy is lost.
10% energy is lost. Yes, that is correct. Or in other words, you supplied 100%, but you got back 90% of the work. So 10% is lost. So the efficiency is the ratio between the thing you are getting and the thing what was supplied. That means power output over power input, right? So let's write it down. The efficiency is power output over power input. And we know how to calculate power output. So I will write down the equation, and here it's power input. Okay. So what can be the maximum? Okay. So if you want to express the efficiency in percent, you can multiply with 100. If you want to express that in just numeric, like the decimal value, you don't have to do anything. Now, what can be the maximum power? What can be the maximum value of efficiency? 100. Like in theory, it can be 100, but obviously you will not get 100. So after doing all the calculation, if you get the efficiency 127%, something is wrong there. Or if you get the efficiency negative 5%, something is wrong there. So the efficiency will be 0, efficiency 100%. Okay. Okay. So that's it for all the theory about the energy conservation. And if we want to do a very quick overview, this is kind of the most comprehensive equation for the energy. This equation can overcome all the limitations of Bernoulli's equation. It can be applicable for compressible, incompressible. It can take care of all the energy addition or all the energy loss in the system, right? Okay, so are we good up to this point? And if you look at the expression here, it's pretty much same expression as Bernoulli's equation, except it has some extra terms for taking care of all the other things, right? Okay, so are we ready to start our class example 15? Let's do it. We have kind of 15 minutes. Maybe we will be almost done. If not, that's okay. So those who doesn't have the class example 15, please select that from the front row. And who will read the class example 15?
The irrigation pump is used to supply water to a pond at B at a rate of 2 feet cubed per second.
Okay, that should be feet cube.
If the pipe is 6 inches in diameter, assume the frictional head loss per foot length of pipe is 0.1 feet.
Okay. So, okay, thank you very much. So basically, we have a pump here, which is supplying water to irrigation field or something like that. You know, for irrigation, obviously, there is a huge amount of requirement for the water. And if the water is not readily available, they pump that from some other places, right? So this is something like that. This pump is getting water from pond A, and it is supplying water to a pond higher than the initial pond here. So they are asking you to find what will be the pump power, required horsepower of the pump. That means you need to calculate pump power in horsepower. Also, they are asking you to find the efficiency of the pump. So everything is about pump here for this question. So what we will do, just like any other class example, we will identify the given values. We will try find out what are the values we need to find, and then we will try to come up with an equation which can connect all the knowns and unknowns. Okay, so let's work on that, and you will help me to list all the given values here. Oh. Okay, given values and find. Okay, so what is the very first given values for this problem? Okay, so it says that Q at B is 2 feet cube per second, but you can see there is no other outlet. There is just one inlet, one outlet. So from mass conservation, we know that this will be Q for the whole system or any point, at any point, right? Okay, what else we know? Diameter of the pipe, which is 6 inches, and we can't work with 6 inches. So we will convert that into 0.5. Okay, what else? And if you know the diameter, you can calculate what? Velocity and the area both, right? So pi r square okay, and you are right, you can calculate the velocity also, Q over A. So you can do that. Is there anything else given for this problem? So I will make a star here, like those were not the given values, but we can calculate that. Okay, what else is given? It is, okay, ZB is 8 feet, right? ZA is what? 0. ZB, it's creating too much problem today. ZB is 8 feet, okay. And we also know the head loss also, right? But there is one thing I want you to notice. It says that frictional head loss per foot length of pipe, okay? Per foot length of pipe. That means if you have a pipe of 1 feet, that will be the head loss. But if you have more than 1 feet, you need to find that, okay? So the thing, I will use a different color so that you can remember that. Head loss per 1 foot is 0.1. What is that? 0.1. Okay. Sometimes you will see they can give you like, okay, head loss is 0.1 foot per feet. So if they just say you this way, it's the same thing. You need to make sure you understand what they are saying. Okay. Also, one more thing they gave you, which is the power supplied to the pump. That means power input was what? 2.86 horsepower. Okay. These are the given values, and you need to find two things. The first one is power output, and B is pump efficiency. Okay. Now we have two reservoir here, so we can get the velocity, we can get the pressure and everything. So there are two options. Either you can like in your mind, there will be two options. Like, should I use the Bernoulli's equation or should I use the energy equation? So which one I should use here? What do you think? Bernoulli's or energy equation? Energy. Okay. What is the reason for that? Why we can't use Bernoulli's here? What is the first limitation of what is the one of the main limitation of Bernoulli's equation? It can't handle the energy loss, right? Or any addition of energy or something like that. So we have pump here, which is the addition of energy. We have loss here. So Bernoulli's equation is not an option here. We need to use, we will use energy equation because there is head loss and addition of energy in the system. Okay, so that's why we have to use the energy equation. Now the solution for A, we needed to find the power. So gamma Q, we need to calculate the power for pump. So I will use H pump. Okay. Now, since this is water, FPS system, what will be the gamma here? There is no temperature requirement or anything. So we can say 62.4 lb per feet cube. What about Q? Do we know the Q here? 2. Now, we don't know the pump head here. Like some of you may argue, ma'am, we know it's 8 feet because that's the distance that pump is overcoming. But that's not true always because there is a loss in the system. So we need to consider that part as well. There's a velocity inside the water. So there are a few things. That's why we can't directly say, okay, this will be the pump head. So what we need to do, we need to apply the energy equation to get the pump head. Okay, so let's do that. I will just write down pump head here because we don't know this one. So let's find out that. Apply. So in between which 2 points I should apply the energy equation? 0 to 8. So that can be C and B. This can be A and B, A prime and B. Which one you want me to try? Or which one will be the correct one? C and B can be correct, but it can be difficult because at C, you don't know the pressure. It's inside the pipe. So one trick part, always choose open surface. That will help you with power, pressure, and velocity. Okay? In between A and B. Okay? Always try to choose open surface. As I said, that will help you with pressure and velocity. Okay? I think I should write down the equation in the next slide because I will need space. So in between A and B, the equation will be obviously PA turbine equals to PB over gamma VB square over 2G and that should be VZB head loss. And I think I should write down its apply energy equation in between A prime and B, because in between A prime and B, there is a pipe. In between A and B, there is a portion, there is no flow or something. So A prime. Okay, let's find out what is the pressure at A. What do you think? Pressure is 0 because PA equals to what is the velocity at A?
Are we assuming the velocity is constant throughout the pipe?
We already know that because the same Q is going, there is no change in diameter. So velocity at any point will be same, but what will be the velocity exact at that point on top of that surface? That is the velocity inside the pipe. At A, this is just open surface. Another advantage, the velocity is almost 0. That's why it's easier to choose open surface. So here again, VA is almost 0. It's not 0, but it's almost 0. What about ZA? The datum is given, so you don't need to choose datum, which is good. ZA is 0. Do we have any turbine in the system? So this whole thing is 0. We don't need, we could skip that part. PB At B, water is discharging into open atmosphere. Again, PB is, what is the pressure at B?
0.
Good. You see, we got so many terms, which is 0. So PB, P atmospheric, and 0. Okay. We can't say VB is 0 because VB is like coming out of the pump, but we know what is VB. What is ZB? 8. And we need to calculate the head loss. We will do that. So let's write it down. The next line. We have just 1 minute. So 1, 0, 0, 0. Wow, we have 3 zeros. Great. 0 plus. We have 0 plus. Anyone has the number for VB? Anyone calculated VB? 10.2. Let's, okay, yeah, I got kind of same. I got 10.186, so which is 10.2. Okay. So 10.2 square, 2 into 9.81. Okay, and ZB is 8. Now for head loss, what is the way to calculate head loss? 8 times. Okay. But the pipe starts from this point. So the total length of pipe is 7 plus 8. Okay. So I will start from this point on Monday. But if you want to get 1 extra point, you can give me the pump head value on Monday. It should be around 10. 10 is not the exact answer, but it should be around. No, I'm not saying that. It will be above 10. One more hint. So try to work on that. That's it. You can give me million answers, but
It says 9.81.
Which one?
You put gravity as 9.81 meters per second squared.
Okay. Oh, that should be 32.6, right?
Yeah,
Oh, 32.2, not the. Thank you. Mm-hmm. Yes.
11.1.
H pump? I'm not saying.
I mean, it's
You all have a good weekend. I'll see you on Monday.